All right, welcome. Wednesday review. Today's a big day. I made a practice exam. It's a 38 question multiple choice exam, and it's up there on Blackboard now. It's very similar to what you'll see Friday. You got to know why it's right, otherwise it's wrong. And that's the thing that is inherent in this meme here. We're going to go through most of those problems, if not all of them, this morning. And so you're going to feel really good when you go take the test, and you're going to go, yeah, it's B. Oh, yeah, it's C. And you're going to have this dopamine rush, like, I got it, right? You're going to be this little person here. But if you don't know why it's B, the answer is never B or A or C. The answer is the chemistry behind it, right? And so you've got to see, why is that question the right answer? Why is that letter the right answer? And why are these other four not the right answer? So always, whenever you've got a multiple choice test that you're studying from, and that's why I really like Alex, because this multiple choice study test is going to set you up and you're going to feel super good. And then potentially you get here Friday and you're looking at the problems and you didn't click with the chemistry. You were focused on getting the right letter. Do you see what I'm cautioning you about? So study this really well, understand why the right answer is the right answer, and then understand why the wrong answers are the wrong answers. Maybe the core electron thing is wrong, or maybe it's a P block and it's got a D orbital in it, and that's ridiculous. So go through the wrong ones and mark out why they're wrong too, and make yourself notes and so on. So that's a really important study skill to do well. So okay. So Alex reports too. So look at that. I mean, we're 63% progress. So we're really coming up on finishing out the course. That's exciting. The next knowledge check is due Thursday night. Okay. So go in there and do the knowledge check. Make sure you get that Alex points, because that's worth 40% of your Alex points, which is 35% of your grade. So it's, all these percentages. It's all in the syllabus. Okay. So here's the practice exam for exam 3. I know it's a little tiny. I know y'all can't see that in the back, but it is on the video, and I'll describe the problems that we're doing. So I just did screenshots of the test, and we'll just go through this practice exam because it'll make sure that we cover all the topics and you guys will be well prepared. Now, why is it 38 questions? Well, because I just kept adding questions. Okay, and the one on Friday, I think it's like 36. I was aiming for 33, so I had 35 or 36. I'm going to leave them on there. They're all still 3 points apiece. And so it's kind of like extra credit. So like if you got everything on the test right, it would be like 36 times 3. Don't ask me to do the math. Okay, so you get a few extra points. Okay, that's what, 109? Yeah, okay, 109. So very good. So let's jump in and look at this. So the first one here, table 1. Oh, what is table 1? Let me go find that. Oh, yeah. I was going to try to put it up on the screen. I'm going to try to put it up on the screen so y'all can see what the table looks like that you get with the test. Okay, so we need a little bumper music or something while I'm looking around on my computer. Somebody hum something. There we go. That's right. That's good. Wait, what? I recognize that. What is it? Was it Andy Griffin? Yeah, that's right. That's Andy Griffin. Yeah. Yeah, very nice. Yeah. Okay. Yeah, that's very good. That's right. I'll need it louder so that mic picks it up. Let's see. Okay, here we go. There we go. Okay. No, that's good. Yeah, I can't see what I'm doing because it's on this other screen, but let's see. Okay, let's try this again. World's most boring video. All right, so then we go back over here. Paste. Okay, good. Got that. And let's go back over here. The answer is C. There was a call-in radio show that had the the call-in program, and you call in the morning show, and the little call-in program show, the little thing that they had for people to call in on, was called The Answer is C. So they would ask some really crazy, impossible question, and they say, and what's your answer on today's contest of The Answer is C? And the person would be like, is it C? And everybody would go berserk. Oh my gosh, you got it right. So you had to be there for sure. Yeah, that's right. Okay, so here we are. So we got, just when the music arrived. Okay, so we've got this. It says refer to table 1. So this is what you're going to have. You're going to have 3 tables and a figure. Okay, just like the periodic table, you can tear the periodic table off. You can tear this off too and use it on these problems. So here's the standard enthalpy table. Here's table 1. It's got the substance. It's got the molecular formula, so you could do reactions, and then it's got the enthalpy values. And I got rid of all the decimal places because that's good enough for me to know if you did it right or not. Okay, so these are to the ones place. That's all good. Then we have the bond enthalpy tables, and so there'll be some questions about that using the bond enthalpy table. And then we also have down here, I went ahead and told you to memorize the electromagnetic spectrum, but I went ahead and put it in here. And so you have all of these things. So you can look and see if something happens, and I say, well, what wavelength is that going to be? And tell me what color that'll be, or tell me what region of the spectrum that's going to be in. And so you have that. Okay. And then over here, we've got one of the energy level diagrams. So we can do the spectroscopy part. So, you can look at the energy levels in zeptajoules, and you can convert those over to joules and convert that to wavelength and convert that to frequency, and to know that the spectral line is a difference in energy levels. So that's the table 1, 2, 3 and the figure that we refer to in the exam. So let's go back up here to the problem. Table 1 contains the enthalpy of formation values for many compounds. Why are there no elements like H2, O2, etc. in that table? So here's the table. See, we've got substances. We don't have any elements. There's no O2, no oxygen, no hydrogen. And our options are, for A, delta H of formation is not defined for all elements in their standard states. Delta H of formation is 0 for all elements in their standard states. The table is small, so the elements were simply not included. D is delta H is infinity for all the elements in their standard states. And then E is Dr. Williams is too lazy to include the elements. And then I told you not to pick that one. I couldn't think of any other options. What do you think? B? Okay, yes. And that's the point of being able to put them in a table, is we need a reference level. We need a place where 0 is. And so all the elements in their standard states for delta H of formation are 0, because we're forming all the other substances from those elements. And so when we do products minus reactants, if we're forming a compound from its elements, it's products minus nothing, because we're acting as if the elements came for free. So we don't have to pay anything to get the elements, right? Energetically. Okay, so refer to table 1. Is the heat released or absorbed when acetylene is formed from the elements carbon and hydrogen? So here's table 1. So here's acetylene up here at the top. And it's plus 227. Here's ammonia. It's minus 46. Here's down here, here's methane. We did some problems with methane, negative 75. Here's water, negative 286 for liquid water, negative 242 for gaseous water. So is heat released or absorbed when acetylene is formed from the elements? Let's just do the problem here. So we take H2 plus 2 carbons, solid. Okay. And this would be graphite, but we don't have to write that. But anyway, we got 2 carbons and 2 hydrogens, and we're forming C2H2 gas, acetylene. and when you have a compound that's written like this, and it's being formed from the elements in their standard states, then this is not just delta H reaction. This is the actual delta H of formation. So that's a particular type of reaction. When you have a reaction where it's just the elements in their standard states on the reactant side, and the product is a single compound, 1 mole of it, then that reaction is the formation reaction, and this is the delta H of formation. So this is a positive 227. Is that what it say on the table? 227? 227. Okay. So what does that tell us right here with this positive sign? It's endothermic, and so it's absorbing heat. So it doesn't release heat when it's formed from its elements. It's absorbing heat. So it takes heat to push this reaction forward. And so this is heat is absorbed. It's endothermic. So we would go with B. And I'll put up here, we got B on that one. Okay, refer to table 1. What is the enthalpy of reaction for the decomposition of 1 mole of calcium carbonate? So here's calcium carbonate. Let's always check to make sure it's balanced. So we got 1 calcium, 1 calcium, 1 carbon, 1 carbon, 3 oxygens on the left, 3 oxygens on the right. So that's great. Oh, DW is taking care of me. Okay, so we need to go and find products, and we need to subtract the reactants. So we go to the table. Let's just write it up here. CaCO3 going to CaO plus CO2. And this is really nice because I don't have any coefficients to multiply it by. So I just take the calcium oxide, so minus 636. This is the product, minus 636. And then I add in the carbon dioxide, the other product. So adding a negative number, so that's negative 394. And then I subtract the reactants. Calcium carbonate is minus 1207. And this is where you're going to make your mistake if you're not being careful. It's minus a negative 1207. Okay, so people drop a negative right there. And that's where the thing gets off. Okay. So somebody have a calculator real quick? I mean, I've got the answer right here. Key up. Save us some time. Okay, end up with 177. And it's 177 kilojoules. Why is it not kilojoules per mole? That's really not part of the problem, but it's an important question. Because this, I've kind of violated my own rule. This is a kilojoule per mole, but it was really multiplied by 1 mole. So the 1 mole cancels this mole, and I end up with kilojoules. So that's where all the per moles went. You multiply them by the number of moles, and all the per moles go away. And you add all that up, and you get kilojoules for that reaction as it's written. Okay. So that's that was 177. That's this guy right here. Okay, so then we have another reaction. This is a combustion enthalpy reaction, and it's balanced too. I was really nice to you on this one because all the we did the balancing on the last exam, and so I went ahead and balanced these. So you got 2 carbons here. You got 4 hydrogens. They come in pairs on the water, so there's two pairs. Then we add up the oxygens. So there's 1, 2, 3, 4, 5, 6. So 6 oxygens. They come in pairs, so that's 3 pairs of oxygen. So we're good. Now, if it says 1 mole of ethylene, let's just say we got to this point and I'm balancing it and I'm looking at that oxygen and ended up it being, I need 5 oxygens and they come in pairs. So I have 5 halves of the O2. If you're balancing this reaction, you would want to double everything. But this is the enthalpy for 1 mole of that reactant. And so we don't double anything. We leave it as 1 mole of the ethene, and we just do the 5 halves of the oxygen. Leave it like that. It doesn't matter because when we do the enthalpies and so on, the oxygen is 0. And plus we want it, we're calculating, we're told in the problem, calculate it for 1 mole of the ethylene. So let's go ahead and get those enthalpy values. I'm going to do this one in a table format. I'm going to say, let's do the products first. So 2 CO2s is equal to 2 times 2 moles CO2s, negative 394. Okay, and 2 waters, and it's gas. You got to pay attention. It's 2 moles. This is kilojoules per mole. I'll just leave the units up at the top so we know that all the units are working. Okay, water vapor. It's the last one in the table, minus 242. That's another place where people mess up. So they just find water and they grab the first number they see, and they end up getting the liquid water when the reaction is gaseous water. So that matters, and you'll be off by like, I don't know, 70 kilojoules. And then we subtract out the reactants, the C2H4 minus 1 mole, and that is the ethylene plus 52. We multiply all those through and add them together, and we end up with negative 1324. Okay. But that's how I do the problems. I do them in table format, so I kind of make a little table and then add it down. Okay. That's the first little screenshot. Are there any questions about any of these questions where I can clear things up for you? And those of you who just came in, I'm recording this so you can go to the video and catch up after class.
So you do your CO2, you do your H2O, multiplied by the moles, and then you
subtract the reactants. Yeah.
You subtract the reactants.
Yeah. Yeah. And this one is a plus 52 from the table. So it's a minus 1 mole, but it's a plus 52 here. And if you look at the table, ethylene has got a positive enthalpy of formation. Okay. Now let's do the same problem, but with the bond energy. So here's the bond energy table, bond enthalpies, table 2. What's the combustion enthalpy of 1 mole of ethylene? So it's the same reaction, and it won't be exactly the same number because these are 2 different methods. The bond enthalpies are made for every possible CH bond, and so ethylene and ethane and methanol or whatever, they all have CH bonds, but those bonds are going to be slightly different. So this would be kind of like an average value for all of the different compounds that you could calculate for. But it gets you close. And this is the one if you'll notice, I got an announcement this morning on Blackboard. I messed this one up in my Excel formulas when I was referring to the table. I got trapped by that O double bond to C. There's the CO2 line, and there's another one that's not, and I picked the wrong cell with my formula. And then I had to correct that and get you guys the correct formula. Okay, so let's take this apart. So we got to break apart our reactants, which means we got to add all those energies. We're going uphill, and then we got to make all the products, and we got to subtract all those bond energies to get that energy back. And so we've got 4 CH bonds. So 4 CH bonds plus 3 O double O bonds. And then we're going to subtract. Here I've got 2 carbon dioxides, and each one of those has 2 carbon oxygen double bonds. Okay, so that'd be 4 O double bond C bonds for the CO2, and then I'm subtracting 2 waters, and each of those waters contains 2 OH bonds, so that's 4 OH bonds that I'm making. So we go to the table and get those numbers. So plus 4 times the CH or HC is 413 kilojoules per mole, but there's 4 moles of that. So I'll just show the units on the first one. and it's 4 moles. And then the O double bonded O is 498. And then the O double bond to C for CO2 is 799. Sounds like I'm in a grocery store. 799 for the O double bond to C. And minus 4 OHs, 463 for each of those. And you add all those up and subtract all the others, and you end up with minus 1288. So that's E. Yes? Speak a little louder. It's okay.
I get confused about the enthalpies for the very beginning one, the CH.
Oh.
Branches out.
Yeah, and this one, I missed, what did I miss? I missed the carbon-carbon double bond too. Didn't I? Yeah, I need to also add up here carbon-carbon double bond. And 1 C double bond C. I'm sorry, when you were talking and I looked at it, I saw that I made the mistake, and I'll come back to your question, okay? So we have a plus a 1 times, and the CC double bond is 614. Okay, good. And then that'll give you the 1288. Okay, so now what is it specifically that is tricking you up?
So the very first part of the equation.
Yes.
The C's and the branching out to the H's.
Oh, this piece.
Yeah,
That piece. Okay, yeah. So this is we're going to get to this in the next part of the course of how to make these pictures. Okay. So this is a picture of the molecule, and it's showing the different types of bonds and what's bonded to what. So it's showing that this carbon is bonded to a hydrogen, and it's also bonded to this hydrogen, and it's also bonded to this carbon twice. Yeah, and so it's the sharing those electrons. And so we were early talking about ionic bonding and covalent bonding. These are covalent bonds. So the electrons are what are valence electrons, right? They're covalent, so they're on both atoms. So the electrons in between those bonds are talked about as being covalent. So the electron between the carbon and hydrogen are both on the hydrogen and on the carbon. And so that's what we mean by covalent bond. Yes.
So is it every single time that the products are going to be plus X amount of moles, and then the information from the table, and then all of the the products will be negative, and then all the reactants will be positive?
For when you're using the bond enthalpies, yes. Okay. Because the table essentially, it seems backwards from the enthalpies of formation table, right? But if you look at the enthalpy of formation table, all those numbers are negative with a few exceptions, right? And the bond enthalpy table, all those numbers are positive with a few exceptions. But no, there's no exceptions. They're all positive. Essentially, all the minus signs have already been canceled in the bond enthalpy table. So that's why the calculation seems reversed, because they've canceled all the negative signs, and so we're adding. It's like it seems opposite, because we're adding up the reactants and subtracting the products. And I don't even want to say that out loud, because you're going to confuse with the enthalpy of formation table. This table here is products minus reactants. I cannot write sideways on this tablet. Okay, so I'm going to turn the tablet sideways. Look at that. It's more than one way to skin a cat. Okay. I don't skin cats, by the way.
Sure. You're never beating the cat allegations.
My gosh, it's awful. I'm still having to read it sideways. That's so bad. Oh my gosh.
If it was easy, everybody would do
I know you heard what I said. It's products minus reactants. That's the CANTS. Okay. And then over here, I'm not even going to try it. On the bond enthalpy sides, it's making and breaking bonds. Okay. So you add the ones you break the bonds. So you add the energies of the bonds that are breaking because you're going uphill. So think about nature as up and downhill. You're going uphill when you break those bonds. So you break all the bonds on the reactants, which means you add them, and then you start making products. And when you make products, you subtract all of those bonds and you go downhill. So energy landscape, that is a chemical concept that you need to have in your head, and that'll really help you.
So it wouldn't be like reactants and minus products per bond. You don't think of it like that.
I don't like that language because you're going to start getting in a bad habit. Yeah, and I just don't even want to use those words because it's always products minus reactants when we're thinking about delta H or delta G or delta S. So there's other things in thermodynamics. There's Gibbs energy and there's entropy. And so those are always products minus reactants. And so we're just going to always keep those phrases together with the delta H, delta G, and delta S of formation and reaction. The bond enthalpy is kind of a unique thing, and so we'll just think of it as a unique way. We go uphill and downhill. So we'll go uphill when we break the bonds and downhill when we make the bonds. Yes, thank you. Okay, we got to move on. Okay, then that was just, I think that's pretty much all we got some calculations for the speed of light with the light waves and stuff. Okay, and just a quick question related to wavelength and speed of light and all of that. So this is just a different form of the equation I had you memorize. So if I see you on campus and I ask you what's new, what are you going to say? Everybody together.
Lamb.
Crickets. What's new? C over lambda. Yeah, that's right. Let's try it. C over lambda. Okay, what's new?
C over lambda.
Oh, that's great. Makes me feel so good. Okay, so that's the equation, C over lambda. You'll never forget it. Okay, and so then you could rearrange this, and this happens to be the right answer here. This is C equals nu times lambda. So yeah, that's okay. And then the delta E, delta energy, the change in energy is equal to H nu. Okay, and so then you could substitute C over lambda for that. So then you have HC over lambda. Yeah. So those are our spectroscopy equations. Okay, so which color of visible light has the shortest wavelength? So Roy G. Biv, remember that? Red is the longest wavelength. So then blue or violet, but I don't see violet. So of this list, it would be blue. Okay, refer to the energy level diagram, figure 1. What's the energy difference between levels A and B? So we got to go find that. So here's A and B. So it's pretty simple. A is 0, it's the ground state here, and B is at 300 zeptojoules. And so I'm looking at the answers, and I'm like, man, that crazy DW, I have no idea what zepto is. I forgot. But look at all those options. They're all 10 to the minus 21, so I guess that's what zepto is. So these are all Z, yeah, zeptojoules. And so it was D, it was 300 times 10 to the minus 21 zeptojoules. Now you have to actually get your calculator out. Okay, so we want to know the wavelength of light emitted when the atom drops from level B to level A. So it's dropping by this much energy, that's delta E, okay, right there. And we want to solve for a wavelength, and we got Planck's constant and the speed of light on our periodic table. So lambda is equal to HC over delta E. And so that's equal to 6.626 times 10 to the minus 34 joules seconds. Okay. And the speed of light, 3 times 10 to the 8 meters per second. And then in the denominator is 300, not 3.00, it's 300 times 10 to the minus 21 joules. So my joules cancel, my seconds and per second cancel, and I end up with meters. But I look at here and I see all my answers are in nanometers. And so I did this problem the other day in class. And so I'm going to do the meters on bottom. So that's 10 to the minus 9. I'll do it the right way this time. Right. So I did it a different way in class last time. So that gives me everything in nanometers. So when I punch that all into the calculator, I get 663. I believe. Let me make sure. Yeah, 663. All right. So there's letter C. And then I can calculate the frequency. Okay, so the frequency is nu. What's new? What's new? There you go, C over lambda. It's on a different page. We're going to do it again here. Okay, so then I have 3 times 10 to the 8 meters per second. And the lambda was 663 nanometers, but I'm just going to change that nano to 10 to the minus 9. Okay, and I get my hertz. Okay, but I'm looking up here and it's petahertz, and so I gave you a hint. Peta is 10 to the 15. Okay, so that's so nice. Okay, so in the denominator, a hertz, an Hz, is equal to an S to the minus 1, a per second. Okay, and this is a per second in the top after the meters cancel. And so that's a hertz on top. And so Hz in the denominator, peta is 10 to the 15. And so I have PHZ here. When I punch all that in, I get 0.45. So that's this one. And then it says, refer to table 3. What color is the light that's emitted when the atom drops from level B to level A? So if I'm looking at that, it says 663. And I've got a choice of blue, yellow, green, red, and violet. It's really kind of between orange and red, but I don't have orange on here. I do have red. So I'm going to pick that one because it's the closest. Okay. Does everybody see the logic there? If I had orange and red, you'd be kind of in a pickle. Orange is at 600, red's at 700. It's not a hard cutoff, but it's between orange and red. So I just took orange off the table, so you had to pick red. Okay, makes sense. Okay, we're going kind of fast because we got a whole bunch more problems to go. Okay, things ought to speed up now. How many valence electrons does phosphorus have? Look at the periodic table. Valence electrons. On the count of 3. 1, 2, 3.
5.
Yay. Okay, very good. And the valence electrons in phosphorus are in which shell? Yeah, so the choices. You said P, but you have to look at the choices, and then you'll be like, oh, it's not P. So I'm not criticizing. I'm saying, yeah, that might be a good answer, but then you look at your choices, and you're like, oh, he must be asking about N. So the shell for phosphorus? 3, exactly. Third row. Well, it's the 3s and the 3p. That's the shell, the 3. Phosphorus is isoelectronic with D. Okay, not the element D, but the letter D. Nitrogen. Yep, straight above. So that whole column, they're all isoelectronic. So all the halogens are isoelectronic with each other. All the noble gases are isoelectronic with each other. At a maximum, an F shell can hold how many electrons? Wow, that was good. I was thinking that would be harder for you guys. 14. So an F shell holds 14. Those are the F block elements. You can't remember, you can count them. There's 14 possible places on that F block. What about the D block?
10.
Yep, in the middle, there's 10. P block, 6. S block. Yeah, great. What are all the possible L values in the N equals 4 shell? Okay, this is a little bit more esoteric problem. L goes from 0, 1, ... up to N minus 1. So if N equals 4, then the range of L values has to stop at 3. Does everybody follow that? So this is the one right here. L can be 0, 1, 2, and 3 if N equals 4. Okay. Now you can figure that out. Another way is that for L equals 0, that's an s orbital. For L equals 1, that's a p orbital. For L equals 2, that's a d orbital. And L equals 3, that's an f orbital. And so we have a 4s, a 4p, a 4d, and a 4f. We don't have a 4g. They actually go GHI after that. But no. Okay, what is the L value for all d orbitals? Remember that S, P, D. So 2. Yeah, S is the 0, P is 1, D is 2. So 2, L equals 2. So, this is, kind of a long test. So we're really moving along on these, and you should just be able to knock them out. What are all the possible M sub L values for the d orbitals? So D, that means L equals SPD, L equals 2. And M sub L goes from -2 to positive 2. So you can go down here and find this one, E. Yeah. So that's the 5d orbitals, and you can put 2 electrons in each. That's why you have 10 electrons in the d subshell. So it all fits, okay? Yeah. How many electrons can only have spin quantum numbers of what? This is the last one, plus or minus a half. Yeah, so I have lots of other options here, but plus or minus a half is the electron spin quantum number. Okay, electron configuration of the valence electrons of an atom in its ground state is ns2 np5. So I'm not telling you what shell it's in, but they have 2 in the s orbital and 5 in the p orbital. This atom belongs into which group? So which column in the periodic table is this one in? Yeah, halogens, because those are over there in the 5th column of the p block. What if it was in p6? Noble gases. What if it was just ns2 and nothing else? Alkaline earths. That's the group under beryllium and magnesium and all of that. Very good. Now this one I put in here to kind of make you research all of these different things. So no 2 electrons can have the same 4 quantum numbers. This is known as blank. I didn't have us written on a slide, but I did say it. So that's why this is kind of one that you get to research on your own, but it's the Pauli exclusion principle. That's what makes us have, only 2 electrons in an M sub L and an L and an N orbital. So the Pauli exclusion principle. But let me go through these others. We're not going to talk about the Heisenberg uncertainty principle. We're not doing anything with uncertainty. But the Hund's rule, that is where we put the spin ups in the 3p orbitals. They get their own orbital before they start pairing up. So that's Hund's rule. We maximize the spin before we start pairing them up. And then the Aufbau filling scheme, that's what we're using to make the electron configurations. And then the Bohr atom of the molecule, or model of the atom, is the sort of solar system model of the atom. So those are all in your book. The ground state electron configuration of iron is, and here's the thing on the test, you may want to not look at the answers. You may want to just do it and then look at the answers. So let's do iron. Iron, we go backwards to the previous noble gas. So it's argon core. Because if you look at the answers first, you might pick a wrong one. You might recognize a part of the problem that's right and miss the part that's wrong. See how you could be tricked? I'm not trying to trick you, but if you do the test wrong, you might trick yourself. So we start with the argon core. Where do we come in? 4s is next. Okay, and then once we're past the 4s, it drops down to 3. So it's the 3ds. So it's 4s2, 3d, 1, 2, 3, 4, 5, 6, 6. 3d6. And now I go down and look at the answers, and I know it's right because I know how to do my electron configurations. So I'm looking at this, and I say, no, it's neon's bogus, krypton's bogus. Okay, here's a 4s2, 3d6. That's what I've got right there. And then I can look up here, I'm like, 3p10, that's dumb. Okay, and then the 4s2, 4d6. Here's where you might doubt yourself, right? But that's wrong because it's not 4d after the 4s. It's 3d after the 4s. And so if you have that little tool that you use, 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p. And so we do the little diagonal lines with the arrows like this. And so I get past the 4s, and the very next one is the 3d. You see that? So I just proved to myself with the little tool, it's C. So this is not right. Okay. Okay, what's the ground state electron configuration for gallium? Okay, where's gallium? Ga, over there by zinc. Okay, so argon core. We come in at the 4s2. We go all the way past the 3d, so 3d10. And then where are we on gallium? We're in the p block, but which p? Back up to 4. So it's on row 4. So we're back to 4. So 4p1. I've never done gallium before. Not really, but is it going to steal anything? Is it going to be an exception or anything like that? No, we're not anywhere close to the half-filled D shell. That's the one that we're going to memorize. Or the almost filled D shell, like the 3D9s. And so this is not an exception, so we'll go with that. And here we have, it's this one, isn't it? Yeah, B. Okay. So what's wrong with this one? This is wrong. The 4D is wrong. So that's wrong. Looking at this one, 3D11, well, that's cute. No. And then all this mess, I don't know, 1s2, 2s2, 2p6, 3s, 3p6, 3d. Here we go. Everything was good up to here, even though it's a little different order than the little tool, but it's not a 4d1. So that's wrong. And here, 3d13, don't select that. If I'm looking through, like you're like, I'm having trouble in this class, and I see you answered that, I was like, you have not been studying. This is so obviously wrong. Okay. The ground state electron configuration of blank is argon shell, 4s1, 3d5. Ooh, look at that. Yeah, it's one of those exceptions. So we got the 3d5, which might make you think it's manganese, but we've lost the 4s, so it's chromium. It's spilled one to come half full. So that's the chromium. Angular momentum quantum number is limited by n. That's that. The angular momentum quantum number is L. It's limited by n. This explains why there are no blank orbitals. So remember, in our handy tool, we didn't have a 1p orbital because n is 1, and so L can only be 0. N minus 1 is 0, so we can't have an L equal 1 because n is 1. So we can't have a 1p orbital or a 1d or a 1f. We also can't have a 2d, and we can't have a 3f. So this is that limitation that's preventing us to have those higher orbitals in the lower shells. So this explains why there are no 2d orbitals. There's a 2p orbital, but not a 2d. We could have all these others. But... Okay, then we get into the atomic trends. Atomic radii generally increase. So I'm not going to look at the answers because I don't want to be confused. I'm going to draw my periodic table here. Look at this beautiful periodic table. Okay, and so what's the atomic radius trend? I'm going to draw an arrow like this. Which direction does it go? If I want to say increasing. It increases down here, right? So francium's the big atom. So this is the big one. And this is the tiny little helium. Okay, so now I can go here and find the things that are wrong. So it increases as we move down a group. Yes, that's right. But from left to right across the periodic table, no. So I know why that one's wrong. And then, okay, up a group. It does not increase as we go up a group, so that's not right. It increases as we go down the group and from right to left on the periodic table. Yes, that one's good. Let's just exclude the others too. As we go down a group, it increases, and the period position has no effect. No, that's not right. Or if it increases as we go up a group, no, that's not right. So I know why that one's right, and I know why the others are wrong. So I'm confident. Okay, we're running out of time. Which of these has the largest radius? Rubidium, strontium, scandium, potassium, and yttrium. So let's find those in the periodic table. Yttrium's down here. It's to the right of rubidium, so it's smaller than rubidium. So it's not this one. Where's potassium? Potassium's above rubidium, so it's not that one. Scandium is diagonal, so it's both to the right and up, so it's not scandium. And strontium is to the right of rubidium, so it's not that one. So this is the one that's the largest. Which equation correctly represents the first ionization? We talked about first ionization potentials all the time, and just wanted to put these in here to enforce that knowledge. And so it's an atom being ionized. So it forms a cation plus an electron. So that's the ionization energy. And so we're just looking for that situation. So this is a P plus. That's not what we want. This is a P plus an electron. That's not what we want. Here's a P minus. We're not starting with a P minus. Here's a phosphorus that loses an electron but somehow ended up negative. That can't be. So it's this last one. Phosphorus, arrow, phosphorus cation plus an electron. So there's our first ionization potential. What about the third ionization potential? So this, I've pulled one off for the first ionization. If I pull a second one off, I get an A2 plus, okay? And then so this is A plus here. And then for the third one, I start with A2 plus and pull that third electron off. So this is first, second, third. So this is the one I'm looking for with whatever atom I'm looking at. So this is phosphorus. So 3 P's? No, I don't want that. No, 3 electrons? No. 3 plus? No, we've gone too far if we're at 3 plus. We're looking for the 2 plus becoming 3 plus by losing an electron. So there's our third ionization potential. And starting with a negative, that's nowhere. We're not doing that. Okay, so then blank have the lowest first ionization energies of all these groups. Which one of those groups is easiest to ionize? We got a vote for noble gas and a vote for alkali metals. So let's draw our periodic table. Okay. Okay, so this has the arrow that goes up, right? And this is increasing IE. Okay, that's terrible. My writing is bad. Increasing in ionization potential. So helium is the hardest to ionize, francium is the easiest. So this is the easiest, this whole group. So it's alkali metals. Okay. This is similar to the, this is very similar to the Alex problem where you had the bar graph. So you had little tiny bars here and you had big bars there. And so we're looking at this and we're saying, how many valence electrons does this atom have? So this is small, and this is big and big. So how many valence electrons does this substance have? Yep, 2. The 2 small ones. Those are your valence electrons, and then you get into the core and it's hard to pull them out. The rest is just radii. Okay, don't forget about the cations and anions. Cations are really small, smaller than the neutrals. Anions are bigger. And then I have one on here from the substances from acids and bases. So we did it. We got through it.
Did you give us a key?
Yeah, the key's on the back of the whole thing. So, all right, good luck, guys.
Thank you.